Okay, so both the session chairs are here in the session, so I think we can start. So, hello everyone, a very warm welcome and good evening to all of you joining us from different parts of the world. Dear authors, the session chairs, and esteemed guests, welcome to the technical session 7C. I am Yashita and I'll be your moderator for this session. On behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you all to the 10th World Conference on Information Communication Systems, Software Security and Sustainability, which is WorldS4 2026. So, this landmark 10th edition of the conference is being conducted in a hybrid mode, while the physical conference took place yesterday in London. And we are delighted to connect with you all virtually through Zoom on 29th and 30th of July. So we have an exciting lineup ahead, and I'm sure we'll have some insightful discussions and innovative ideas. So before we start, a quick session guidelines. So we will be having six paper presentations scheduled, and each presenter will be given 12 minutes for their presentation, followed by 2 minutes for question and answer session. And at the ninth minute mark, I will be giving a gentle reminder to everybody so they can wrap up comfortably. And we kindly request everyone to stay connected with us until the closing remarks. And if you have any questions, technical issues, or updates to give during the session, please feel free to use the chat box. Me and my co host will be addressing them. So before we begin, it is my honor to introduce you all to today's session chair. So we have Dr. Basant Tiwari, who is an associate professor at MIT World Peace University, Pune, India. He has published extensively in reputed national and international conferences and journals, a senior member of IEEE and ACM, and a life member of CSI and IACSIT. He also serves as a reviewer for several prestigious international journals and books. His research interests include information security, pervasive computing, healthcare informatics, and machine learning. So, Dr. Basant, welcome to the session. Do you
Thank
have
you.
something to say to start the session?
Yeah, thank you, Vanshi. Thank you very much. Yeah, your name is Yasista.
Yashita, Yashita, sir.
Yashita. Okay, thank you very much, Yashita. And first of all, good afternoon and good evening to everyone. It's my honor to be the part of this conference, the renowned conference. Uh, and I want to thank each and everyone associated with this conference. I warmly welcome to each and everyone present in this conference or in this virtual room number 7C of 10th World S4 2026 conference. So in this session, we have six papers, uh, very interesting papers that are covering AI, agriculture is there, then cybersecurity, finance, IoT, and industry 4.0. So I hope that everyone will enjoy these presentations. So I think everyone should let us begin, or then we will see. We will follow each and every rule that is given by Yashita and complete the session. Thank you very much. Over to you,
Thank you
Yashita.
so much. Yes, sir. Thank you so much for those words. So, our second session chair for today is Dr. Prince Kelvin Owusu, a lecturer in the Information Systems Department at the Ghana Communication Technology University. His core research interests encompass digital game-based learning, information security, cybersecurity, the Internet of Things, and educational technology. Dr. Ovsu has authored more than 28 peer-reviewed research publications. So, Dr. Kelvin, do you have something to say or should we proceed?
All right, good afternoon. Sorry, my camera is just off, but I want to thank everyone for the opportunity, and I want to thank all the presenters this afternoon for the opportunity to present your papers. And we believe it's going to be a very powerful time, and we are happy to have you all. We welcome you all to this conference. So thank you. Since the first author has already spoken, I would just like to pause so we can start with the presentation. Thank you.
Thank you so much, Dr. Kelvin. So, we will move with the first presentation for today, and we have Vedika Dhende. So, Vedika, are you present in the session? Okay. Any of her co-authors is present on behalf of her?
Hello, am I audible? Hello.
Yes, Vedika, you're audible. So she is here to present her paper titled as Agri-Diagnosis, Plant Disease Detection and NDVI-based Crop Health Monitoring. So, Vedika, you can start sharing the screen.
Sure, ma'am. Thank you. Hello, is my screen visible?
Yes,
Actually, the presentation is not visible, but the meeting is visible.
Okay, just a minute.
So what you can do is, when we share the screen, when we click on the
Hmm.
share button, there are multiple tabs which are open already on the computer. Yes, I think yes. So it's perfect now. You can start.
Okay. So, good morning, good afternoon, good evening, everyone. I'm presenting Agri-Diagnosis, a system for plant disease detection and NDVI-based crop health monitoring, developed with my co-authors at Walchand College of Engineering, Sangli. In short, this system brings together two things. Farmers usually have to check separately whether a plant is diseased and how healthy their field is overall. So we can do this using a CNN for leaf level disease detection and random forest model for NDVI production. Let me walk you through the problem, our approach, and our results. Let's start with the problem. Manual crops inspection is slow, and by the time a farmer notices a disease with the naked eye, yield loss has often already happened. The tool that exists today work in isolation. On one side, disease detection app looks only at the single leaf. They have no idea what's happening across the rest of the field. On the other side, NDVI platform gives you a macro satellite level view of vegetation health, but they can't tell you why a patch is stressed or what disease might be responsible. Agri-diagnosis closes that gap. It's a single web dashboard that combines CNN-based leaf disease detection with farm-level NDVI monitoring through Google Earth Engine. So a farmer gets both the things: what's wrong with the leaf and how is whole field doing in one place without needing any technical background. So our work builds on two established research threads. First is NDVI itself. Uh, it's widely recognized in remote sensing literature as the most reliable indicator. Second, on the computer vision side, deep CNN architectures have proven highly effective at classifying leaf disease from images with strong accuracy on real world datasets. But here's the gap we identified. Commercial tools like Plantix do diseased classification well, but ignore field level context. NDVI platforms do the opposite. Nobody had put both of these together in one unified system. And that's exactly what agri-diagnosis does. So methodology is, here's how the system is structured end to end. A farmer interacts with the platform in one of the two ways. First, the plant disease detection module. They upload a file, leaf image. Our CNN classifies the disease and system returns a treatment and pesticide recommendation. Second, the NDVI crop health monitoring module. The farmer draws their field boundary on a map. We pull environmental data through GEE. Our random forest model predicts the NDVI value and we render it as a color coded map. Both modules feed into a single uh, page, so the farmer sees disease name and treatment, pesticide recommendation, color coded field map in all in one screen. Now let's look at each module in more detail. So, starting with the disease detection pipeline, we use the plant village dataset from Kaggle, which is collected and pre-processed for training. We trained a CNN using TensorFlow and Keras for image classification, then deployed that trained model as a Flask microservice connected to our Node.js backend. When a farmer uploads a leaf image, the model predicts the disease class, and we immediately fetch the relevant treatment and pesticide recommendation from MongoDB. So end to end, from upload to actionable advice, this happens in seconds with no manual lookup needed. Next is NDVI crop health monitoring workflow. Step 1, the farmer selects the state and they draw a polygon directly onto the map of the uh, exact boundary. This keeps the analysis focused on their land, not the surrounding area. Step 3, those coordinates go to the backend, which connects to the Google Earth engine to pull land surface temperature, evapotranspiration, and precipitation data. Step 4, we feed that into a trained random forest model, which predicts the NDVI value. And step 5 is we render it back as color-coded map with green for healthy vegetation, orange for moderate stress, and red for the higher stress. The next is the data collection. To train the NDVI prediction model, we used a large environmental data set from Kaggle, over 1 million records spanning many trees, which let the model learn seasonal patterns rather than just a single snapshot. The data set includes NDVI values alongside three key predictors, that is LST, evapotranspiration, and precipitation. Everything was processed in Google engine and resampled to a common resolution, and we ran it through noise removal, missing value handling, normalization, and filtering. For training and evaluation, we split this into 80% training, that's about 838 uh, 860 samples, and 20% training, that is 2,09,715 samples, using split so that distribution of each variable stay consistent across both sets. The next one is the ML training and evaluation. We didn't just pick one algorithm. We trained our and compared five linear regression, random forest, XGBoost, ANN, KNN regressor, all on the same trained test plate for a fair comparison. Random forest came out on the top,
Vedika,
and
sorry to
yes,
interrupt. Just a quick reminder that you will have to wrap up in next 1 minute because the time is already up.
okay, fine. So
Yes.
the next working of the random forest, each tree learns simple threshold rules like for example, if LST is below threshold, go left, else it will go right. And these splits are chosen to minimize the prediction error. Since this is a regression problem, the final NDVI prediction isn't a majority vote like in classification. It's an average of all the individual tree prediction. So this is how our random forest for NDVI prediction works. And this is Google Earth Engine, where user draws a polygon, coordinates are sent to the backend, GE API queries on the various data sets, and we get values of land surface temperature, evapotranspiration, and precipitation uh, after the processing, like cloud masking, clipping, all those things. And this goes as the model input. Now, the backend script handles all these things pre-processing, and the payoff on unseen field level test data, we got achieved r squared of 0.945 and RMSE of 0.53 with the mean average error as 0.017. So here are our results. Linear regression trains significantly with a R squared around 0.58, confirming that NDVI simply can't be captured by a simple relationship, linear relationship. XGBoost and ANN both perform well in 0.93 and 0.94 range, but the random forest edges out them with the highest R square of 0.95 and the lowest RMSE and RAE. And critically, when we look at the generalization, our random forest scored 0.9923 on the training data and 0.9945 on testing data. That's small. Healthy gap tells us that model isn't overfitting. It learns genuinely patterns and hold up to the data it's never seen. So this is what the farmer actually sees at the end of the process. An interactive field map, color coded exactly as I described earlier, green for the healthy zones, yellow for the moderate stress, and orange for the high stress. So, because the farmer already selected their state taluka and drove the field polygon, this map is specific to their land, not a generic regional average, and it's generated instantly so that can act on the same day. So these are the references which we did study on and conducted our study. And in to wrap up, agri-diagnosis brings leaf level disease detection and farm level NDVI monitoring together into accessible dashboard, something existing tool doesn't. Our CNN identifies plant disease from uploaded images, and our random forest model predicts NDVI with 94.45 percent accuracy on the unseen data, and the closeness between our training and testing scores confirm that model generalizes well rather than overfitting. Most importantly, we build this to be simple enough that any farmer can use it without technical expertise, turning satellite data and machine learning into a same day actionable decision at the field level. And thank you for listening me patiently. I'm happy to take any questions.
Do any of the session chairs have any questions for her?
Okay. This is Vedika, right? So Vedika, I have your presentation is very good. Your work is also very good. I want to ask you only one question. Have you checked the reliability of NDVI based health monitoring, since it is checking the health of the leaves or the plants, right? So
Yes, sir.
yeah. So have you checked the reliability of this monitoring system in different lightning, different weather, or different crop growth conditions?
Yes, sir. We actually implemented this using data of different type, like cloudy weather, sunny weather, and it outperformed over there. So
Okay.
yes, we tested over there.
Okay. Thank you. Thank you very much. Over
Dr.
to you,
Kelvin?
Kelvin, sir.
All right. Dashita, who is the presenter? Vedga,
Vedika,
thank you
it's
very yeah,
Vedika.
Vedga, thank you very much for your presentation. That was a very nice presentation. And your slides are also on point. But I want to find out how effective is the methodology that you use in collecting, gathering your data. How effective is it? The Kelga
Sir,
method you use, how were you able to use it to collect your data?
sir, actually, the data collection part which we did for agri diagnosis was we took the data like plant village data set which was available on the uh, which was pre-available on the Kaggle platform. So there we from there we took the data set, and yes, that is the platform from where we collected the data because it was the huge data. So we took the pre-available data.
Data. All right. So how effective was the approach in what analyzing the data for you? To
Yes, sir. I'm not getting. Hello.
I'm saying how effective was the Kiga program in running the data for you to be able to get your output or your results? How effective was it?
Sir, actually, talking about the data which we got was
Yeah.
actually some sort of pre-processed data, and like added, we like did pre-processing on our side also, like cleaning the missing values, like normalizing the values, dropping existing columns which were not required, then doing feature engineering. All these things we did on pre-processed, we did on the data, so to make it suitable for ourselves.
All right. Okay. Thank you. Thank you.
Thank you so much, Vedika, for your presentation. You can stop sharing.
Thank you so much.
So, our next presenter for today is Romildo Silva. Sir, are you ready?
Okay, thank you very much. I'm ready. Can you
Yes, so he is
listen
here
me?
to present his work titled as AI Agents and Financial Information Quality Across Traditional and Tokenized Financial Ecosystems. So, sir, you can start presenting.
Okay, I'm going to share my presentation. Can you see my presentation?
Yes, sir. It is perfect. You can start.
Okay, thank you. I'll try to use my 12 minutes. Okay, as said, AI agents and financial information quality. Our work, as said by the chairman, my name is Romero Silva, and my colleagues Maria Tavares are present here in this session, Filipa Silva and Carmen Vox from Portugal. We are from Gaia High Polytechnic Institute, and Maria Tavares, our colleague, is from Aveiro University, my teacher. Good afternoon for all who are around the world. Good evening, all. Let me see. Okay, our agenda is going to motivation, the methodology, some results, discussion, and conclusions. Okay, the motivations is that tokenized RWAs, real-world assets, and AI agents are reshaping how financial information is produced and consumed by all the people on the automated programs. But how the financial decisions are only made, but good and bad information behind them. Okay, so the research question is, how does the diversity of traditional and tokenized financial data affect the reliability of AI agents operating? Let me see, because this, okay, it was in front of my words. Operating in rural assets ecosystem. Okay, the background is about tokenized finance, autonomous agents, and the overall questions and data quality. We don't have enough time to talk about some points, but we have to say that blockchain infrastructure let traditional assets be represented as tokenized real assets. They are WAs. And AI agents increasingly automate financial data retrieval and analysis, comparing with the humans. And yet, their information quality is rarely assessed, we think, is the hypothesis of the work. We see the gap that raw market data compared with evidence of information quality for AI consumption. We have the AI working all the time, but about the quality of the data they consume, okay? We see the opportunity that to do a quantitative, reproducible, and way to compare traditional vast tokenized data quality. It's the objective of the work. The methodology is a quantitative Python-based AI agent. So we used Python to produce AI agent to compare the data quality. This work is all automated by the Python, and we using them packages and stores of features. And statistical behavior of traditional and tokenized financial assets. Okay, the program will collect, assess the quality in each base available, describe the data, test normality and robustness, all them in the Python autonomous. Okay, the asset studied, it was defined only two traditional ETFs and two tokenized assets to compare the data. We highlight that the importance of the work is not the quantity of the assets, but what we can see about the data the AI agents consume from the different sources available. Okay, SPY and KKK are ETFs from the TradeFi economy, and PEX and Ondo are tokenized assets. There's some information about the asset study. SPY is a traditional finance, the largest ETF in the world, tracked by the S&P 500 index, one of the world's most liquid ETFs. Triple K is among the world's most liquid ETF too. Technology-focused ETF tracked the Nasdaq 100 index. The bar are from the traditional finance. From the tokenized world, we have tokenized commodity AX. PAX Gold is a tokenized gold-backed digital asset. Okay, each token represents physical gold. The price is similar to the gold, bridges commodity and blockchain. Tokenized RWA systems and native token of the Ondo Finance. Ondo Finance is one kind of crypto assets. Okay, focused on RWA tokenization. All assets traded in the Ondo Finance are tokenization of assets from the real world. Okay. We defined the hypothesis H1 and 2. Hypothesis 1, tokenized asset have greater informational and statistical variability than traditional assets, is one. And hypothesis 2, tokenized assets will return deviate more strongly from normality than traditional assets, is what we want to test, okay? They propose that the AI agent framework follows this sequence, okay? Financial data source, we use the Yahoo Finance APIs, ATFs, and RWA. And for all them, we have information in Yahoo Finance, and we did other API we used it before. Okay. Perception, automated data retrieval API requests is the perception from the data. Then memory is raw data storage, which we treat with CSV and metadata from the perception data. And reasoning, we talked about the quality metrics and statistical made with the data. Okay, with the outputs from the Python data obtained. Okay, the action is the outputs, tables, figures, analytics outputs. Okay, we must to highlight that although implemented in Python, the system behaves as an autonomous AI agent because it continuously acquires financial information, evaluate data quality, perform statistical analysis, all born in the package, okay? And generate analytical inputs without no one human intervention, okay? So the Python-based implementation is a retrieve, compute, describe, generate data. And the test is there in the other side, normality, robustness to generate data violated in this implementation. Okay, total relative time in median near 8 seconds. Okay, at the time of API request, in average 2 by assets. We have 4 assets in 8 seconds. Okay. Okay, we defined these metrics. From each asset, it was calculated latency, completeness, null rate, and data volume. We must do the latency in seconds, in times, the completeness and null rate in percentage rate, and data volume in bytes. Statistical analysis was made some descriptive statistics and normality and robustness, like Shapiro from deviation normality, Jack-Berra skewness and kurtosis, Levin test to homogeneity and variance. Okay. Revisiting the hypothesis, we want to know that if the tokenized asset show great information statistical variability and see if tokenized return deviated more strongly from normality. Okay, the data, we can see that the evidence of online data retrieval, we highlight the sources by SPY and Yahoo Finance, Pax Gold and London, CoinGecko API, and CoinMarketCap API, all autonomous to take the data. We highlight the data quality metrics computed by AI agent in the right above. That bytes measure the size of the APU response, not the asset itself. Okay, the time of byte, that's the API response. It's like SPY 19,000 bytes, okay, and other examples that we see there. We have more 2 minutes. Let's see. This graph compare traditional and volatility of the Ondo and shows that the Ondo have more volatility. Okay, it's then the SPY in the in resume. The Pax Gold and Ondo have more volatility than the traditional assets. Okay. We must talk about the Shapiro test because they test the normality of the data and the tokenized assets showed strong deviation from normality. Okay, Shapiro show that tokenized have more deviations. Jacques Behar confirms it because it's on how explain the Shapiro wheel. Because there is stillness and kurtosis, we confirm that no normal behavior identified by Shapiro wheel. Okay, enforced the present emptiness and scarce kurtosis, and then so test the equality of variance, confirmed significant difference and return variance, and tokenized assets with higher volatility dispersion. Okay. The discussion about we have a framework, statistical validation we talked about, comparative evidence, quantitative comparison of quality across traditional we said, okay? The conclusion is that AI agents can operate reliability across both traditional and tokenized financial. Our agents take data from all them. Tokenized data show great availability, as you talked. And we highlight only to finally rather than proposing another analytic model. This study demonstrates how autonomous AI agents can become active participants in financial information ecosystem, continuously collecting, evaluating, and transforming heterogeneous data into actionable knowledge. Okay, thank you very much. I think it's the final.
Oh, thank you, Romildo. Thank you very much for your nice presentation.
Okay, thank you.
Sir, I have only one question. Your work is very good since you develop an AI agent. So have you, that means I want to ask you that, have you checked your results against hallucinations?
Hallucinations?
Yes, because you made the AI agents, right? So
okay.
Have you got some results that is not looking a real kind of thing?
Okay, we think the answer is how we use the Python to do this. Okay, the agent is programmed in Python, and the data is collected autonomously. We think one problem you can be questioned is if you have we call them AI agent, but we don't use LLM. Okay, you don't use a large language model. It's only it can't be it's a AI agent because they autonomously do all them, including the test, statistical test, but it not use a large language model. Okay.
I got it. I got it. You are not using LLM. I got it. But in your that Python, because you are using the data, that is data set, right? You are using Yahoo data set. So in that also you didn't find some different kind of behavior of your agent.
Where
Bias.
we find the difference?
Yeah.
Okay, the difference is because when we collect the data, they put them all them in the Excel data as CSV data, okay, and you can see all them. That because the statistical test is made, and we all data are retrieved and collected to being available, as we can see over time, and we repeat the procedures after if you want.
Okay. Yeah, it's okay. It's okay.
Okay.
Yeah. Thank you very much. Thank you.
Okay.
Thank you. Thank you.
Good afternoon.
Yeah. Over to you, Kelvin, sir.
Dr. Kelvin, anything to say? Okay.
I think I'm okay. It's good.
Yeah.
Good.
Okay,
Thank
okay,
you.
sure.
All right.
So let's move forward. So next we have GM Trupti. Are you present in the session, Trupti?
Yes, ma'am, I'm here.
Yes, so she is here to present her paper titled as AI-driven IDS for cloud infrastructure and adaptive and scalable ensemble framework. So you can start, Trupti.
Okay, ma'am. Just give me a second to share the screen.
Yes.
Yeah, is my presentation visible to all?
Yes, it is visible.
Yeah, good afternoon and good evening to everyone present. I'm Trupti here to present the paper AI driven IDS for the cloud infrastructure. So let's start with it. When it comes to part of the reason why we need this is like cloud adoption has expanded in previous year, and it has also invited n number of attacker surfaces. Over 4% of cloud infrastructure suffer from these attacks every year, and 80% of the security systems uh, fall into the trap of uh, finding out on the false positive. So like dangerous attack like buffer overflow and rootkit are like 1% of these attack traffic, but they go completely undetected because of the false positive that shows to the security systems. So the core issue that the traditional IDS struggle is that it is not introduced with the new attack types, and there are n number of class imbalance that's there. So what's required over here is an adaptive, scalable, and real-time ideas for the cloud environment. Here are the previous works that has worked on this particular IDS systems previously in parts. So we have a hybrid IDS system, ANN plus XZ for the imbalance ITO bot net detection thing. So all these papers, they lagged in false positive. They were more mainly impacted with the false positive and with the scalability issue. So the project that we I am presenting has kind of solved these issues. So the data set that I have used is KDD cap 1999. The reason for this data set is that it has 41 dimensional feature vector, and it has normal traffic and other four types of traffic, that is DOS, prob, and R2L and U to R. Moving on with the pre-processing the data, the first step goes with the data cleaning and then standardization and dimension reduction. For the dimension reduction, we have used PCA, where 38 numerical attributes were converted into 25 principal components by retaining 98% of the important information. And for the class balancing thing, we have used broadline moth, uh, where broadline moth. Moving on to the next so the architecture that we have proposed is, it contains of 7 layers. Let's get into the architecture diagram to understand it well. First we have the input layer.
Okay, go ahead.
Hello.
Yes, yes, go
Yeah,
ahead, go ahead.
am I audible?
Yeah,
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 we
you are
have
audible, Trupti, yeah.
first layer, we have the network traffic layer, where the raw data is being injected. Then the pre-processing layer and the feature selection and encoding layer. Over here in the feature selection encoding layer, we come to be part of PCA. as I said before, where 38 attributes were converted into 28 components by retaining 98% of the important information. And next layer we have uh, balancing the layer, where we use broadline smart. So the balance data is then injected into the classifier. We have three classifiers, that is decision tree, AdaBoost, and XGBoost. The data will be injected into these models individually, and the individual results of all the three individual models will be then injected into the max voting assembly, where the max voting assembly takes the vote of maximum and then gets you the output. So the reason why why to select why we have selected the decision tree, AdaBoost, and XGBoost is the decision tree is very interpretable, and it is rule based, and it gives you the accurate results of the proper labeled data set. Whereas tuned AdaBoost, it is sequentially weak learner, but it catches the rare attacks that comes into it. And we have XGBoost is the reason to use XGBoost is mainly for the scalability and for the runtime performance, for the when it comes to part of real time uh, approach, like real time action. So the results of the individual model and assembly model, here are the results. So let's get into the decision AdaBoost, tuned AdaBoost results specifically. So the reason why the AdaBoost was specifically tuned was because the default model settings didn't give enough accuracy, whereas this was tuned with 200 estimator and learn rate of zero point 0.1, and the parameter space of n estimation of 50, 100, and 200. At the end, the final selection got us 200 estimators and with the zero point 0.1 of learn rate. Here are the result matrix of decision tree, XGBoost, and the max voting assembly. With coming to the part of decision tree, we have 32 false negative and 50 false positive. Whereas coming to the part of XGBoost, we have 5 false positive and 18 false negative, which is really good. And when come to the part of max voting assembly, we have only 11 false positive and 18 false negative, which shows which is strongly reliable. And when you compare with the individual models, this shows a better uh, success in the matrix. For the model evaluation, we use accuracy, precision, and recall and F1 score. Here is the matrix of the individual models of decision tree, XGBoost, and AdaBoost, and also the model evaluation matrix of max voting assembly, which combined the result of all the three individual models. So here you can see that the accuracy compared to all the other models, the F1 score is good with 0.9994, and recall of 0.99, and with the precision of 0.998. To conclude it, the build model, as far of now, has achieved the accuracy of 99.94 accuracy, and output, and the borderline smart along with the max voting assembly has outperformed every single classifier of IDS method. And coming to the part of scalability and reliability, this model is better because of the ADA boost and the XZ boost, which gives you the real time application and data injection flexibility. and the future work would be in the part of hyper tuning the decision tree and XGBoost also, which I feel would improve the model accuracy when it comes to part of real time detection. And the next future work that we are looking into is for the scalability and integrating it with the cloud environment. Yeah, thank you. Thank you. That's the end of my presentation.
Yeah, thank you very much, Trapti. I have two, three suggestions as well as some question with this presentation. First of all, I want to ask you that you use the data set of KDD Cup, right?
Yes,
99,
yes, sir.
right? So it's, it's very old, around 27 years old data set,
Yeah.
KDD data set, right?
Yes, sir. Yes,
So
sir.
if you are using that particular data set, so how you will get the better accuracy? Because this is very old data set. Nowadays, we have the DOS attack data set and so
Yeah.
many data set
Yes,
that
sir.
is already publicly available. That is from Canadian Institute of Cyber Security. They have CIC IDS data set,
Okay.
right? So you must have to work on that. That
Okay,
is
sir.
better. So they have CIC IDS data set of 2017, 2019, 2023. They have a latest IoT data set also. So
Okay.
you can use for your further or future research whenever you will fine tune the random forest. Yeah, you are using random forest, yes?
No, sir. Decision tree.
Decision tree.
Yeah.
Okay, decision tree
Yeah.
with XGBoost when you will do. So that at that time you should use that thing. That will give you the better result.
Yeah. Sure,
So
sir.
they
Sure.
have a better data. They have so much data. Now,
Okay.
next question I want to ask you in this KDD cup data set, where you find the class imbalance? Where you find?
Uh, Okay, so the thing is, in that data set, we have normal traffic and we have other four categories.
Mm-hmm,
So the categories like R to L and U to R are minor classes.
mm-hmm.
So like when I looked into the data set, they were the minor classes.
Okay.
Like I shifted with a number of techniques for the class balancing,
Mm.
and smart. I mean, borderline smart was the best for the suited, as it created the data points near to the decision boundary. So the model that's the point where the model normally goes into confusion or to the hallucination part.
Okay, so have you checked that the accuracy before applying the smart or after applying the smart, before creating the synthetic data and after
Yes.
creating the synthetic data, what was the difference between them? Because you have not shown the result of those before smart and after smart.
Okay. So like the data, like before the KDD data set, I worked with the different data set, but
No, no, I am talking about this with the KD data set. You are applying smart
yes,
for making the class balanced.
yeah, yeah.
Right. So I want to ask you, have you checked the accuracy before applying the SMOT when the data was imbalanced and after data was balanced, that is after applying the SMOT?
Yes, I have checked. At that point of time, the model was like over biased over the normal traffic. So it was giving more false positive for the normal traffic.
Mm-hmm.
Whereas when it comes to the part of the rated traffic, like as I mentioned, R to L and U to R,
Mm-hmm.
over there the model was not detecting the traffic when it came to the part of like training, testing part.
Okay. And what was the size of data set, KD data set? What was the size of KD data set?
There were around 21,000 of variables over there, the categories.
Categories means features or instances?
It was features.
21,000 features. Are you sure?
Yeah, like you're asking the like
Yeah,
rows and the columns, right, sir?
yes, yes, yes. Features means columns, right? Instances means rows.
Okay, okay. Sorry, I was not. I didn't get it at the first point.
Yeah.
So there were around, I guess, so 20 columns, and when it come to part of rows,
Mm-hmm.
we had some. I don't know, we had some 21,000 of rows present. That was the data set which was collected.
Okay. And your title is saying that you are providing AI-driven ideas for cloud environment, right?
Yes, sir.
So when have you checked the overheads for cloud? Because you prepared the ideas for cloud infrastructure or cloud environment.
Okay.
So have you checked that computational overhead and false positive rate that your ensemble framework introduces in a large scale, we can say the cloud kind of environment?
We have not
Because
deployed it into the cloud infrastructure or tested it into the cloud infrastructure. That is our next future work. But the reason of
see,
selecting.
see what I want to say, if you are writing in your title for cloud infrastructure, so
Okay.
what you must have to do, ultimately you must have to simulate the cloud over a cloud simulator or NS2 simulator, because you are writing cloud for cloud infrastructure. So you must have to implement this model over the cloud, then your title will be justified.
Okay, sir.
Got it or not? Because you are writing AI driven ideas for cloud environment.
Okay.
So where you have checked over the cloud environment, how it is working over the cloud? Is it working properly over the cloud or not? Because when you will implement this particular model over the cloud, so there will be some overheads,
Overhead. Yes, sir.
right? So that also you must have to check if you are writing this particular title. Otherwise, it is a simply we can say machine learning based or machine ML based or AI driven based idea system.
Okay,
Got
sir.
it. But
Okay, sir.
for the next time when you will improve, you must have to check the overheads if you are including cloud, as well as I will suggest you to use CIC IDS dataset for that.
Okay, okay, sir.
Okay, because this is very old data set, right?
Okay, sir.
So it will not give you the good result. This is all from my side. Thank you very much. Now over to you, Kelvin sir.
Dr. Kelvin, do you have anything to say or should we go ahead? Okay, I think there are no questions. So, our next presenter is Y. Zamaripa Rivera to present his paper titled as Design and Implementation of an ESP32 based multi-zone monitoring and control platform for plant cutting propagation. So, sir, are you present in the session?
Hello.
Yes, Rivera. Please share your PPT,
You
please.
can present, sir. Yes.
Okay.
Okay, before starting, I will request all the remaining presenters to please wrap up the presentations in time, as we are time bounded and need to finish all the presentations in the given time. So yes, you can start, sir.
Good morning. My name is Joan Samaripa Rivera. They're from Universidad Autónoma de Zacatecas. Today, I have please of the pressing or war aided design and implementation of an ESP32 based multi-zone monitoring and control platform and plant coating propagation. In his paper, we present el design, implementation, and experimental validation of platform-based and ESP32 for automatic monitor and control chamber and propagation by CUT. La propagation by CUT is why use technical because in the house plants multiply while pressing the generic characteristics Over there, the routing string could have very setting to elemental condition, variables as temperature, relative humidity, and irrigation direction influence road, the level, even small environmental variables can uh, cause water stress and register percentage on routing. That's all the level of IoT technology and low-cost platform such the ESP32 is now possible to monitor and control these variables in real time. The in the Y, the C propagation chamber, the GSP uh, 32 has control unity in the sensor and actor responsibility for making in sustainable microclimate in the level of the crude based on the based in this context. We deliver multi-zone monitor, capture or monitor the extreme elemental, the red zone y red zone, autumn the direct current, number system for smart agriculture must only monitor the general conditions of the greenhouse. This limited the ability to know how temperature and able website different zones the propagation chamber. Therefore, the need for as the level the low cost platform to how our multi-zone monitoring automatic control. The objective of the work was design, implementation, and variable platform based the ESP32 capture, the monitor, the experimental evidence, the steam zone, and rod zone, also integration automatic control, local, local data stranger, Wi-Fi communication, and supervision stranded the white side interface. This side present comparison the by previous words and the postal the level in the race. In construct or process incorporation the margin in the different zone extremate every time slam zone y rod zone. Indentation, integration, automatic control, local data extension, y WhatsApp takes wide interface and experimental validation during to 15 campaigns, serían 2 campañas. This characterization allow more complete characterization of the microclimate in the propagation chambers of them. Sistema and agriculture. This figure show the overall agriculture of process platform. Starting of the site, the is control the system reset information from the environmental sensor. All this information is sent the ESP32 Y is the course of the system and responsible for processing the data and exclusive the control strategy. The system controls the different actors responsible for irrigation, ventilation, air extraction, lighting, y thermal condition. Use the vector model. Finally, of the right-hand side, the platform provision data visualization, the embedded website or web interface together to agriculture integration monitoring, control, and supervision the wide and single embedded platform. System components. This I summarize the hardware components and the platform, the ESP condition central, the process and control unity, and sensors, BDish 11, etc. And in addition, the environmental monitoring, the platform is competent and the website. The imaging correspond presented of the interface. At the lobe, the elemental variables measured by the sensors are showed in their time. In the mild sensor is possible the configure the thermal control system and hence the PWM system and signal the use for the Pater model. At button actors, can you monitor the device? Can you control manually? Lighting the configured and CSP files generated during experimental campaigns. The can do during loading in the terminal of the controls irrigation operated the
Sir, there is a quick reminder for you.
why ventilation and extraction there's those based on off control.
Zairovin, can you please show me the result only?
Yes.
En la parte estructural, schematic diagram
Zairovan, are you able to hear
del
us?
system.
Zairovin,
System and
are you able to
prototype
hear
broad.
us?
The 11, the performance of the platform to experimental campaigns we current with addition by 5 days session. During this days, some monitor the experimental control, the system some, the erosion and condition elemental variables operationals, the short lifetimes y water flow, actuación de PWM y signa de records. Se movió.
Thank you, Zairovin, for your presentation. Your presentation is looking like a project. It's not looking like a research work.
Ya cortó.
Right? Is it
Creo que
project?
se movió la presentación. Estoy a 2 de terminar.
Are you hearing me?
Dice, el siguiente son el diseño modelo físico.
Sir, I think he is not
Y
able
el
to hear
elemento de
us or maybe
resultados. Estos serían
understand
los
us
resultados
also.
experimentales.
Yes.
Mm.
So
No
thank you
sé.
very much, Zairovin. I think thank you very much for your presentation. Are you able to give the answer in English?
This table summarize de mayor atención de resultados obtenidos durante las experimental campañas. Icons be sent the platform agents the domains stable temper y the root zone. The result indicates two-head system was able to header the differential microclimate better the experimental, environmental, and propagation zone y favorization o condición for drought elemental. En este caso son
Zamaripa,
los results experimental
can
de los
you
periodos
just
May
summarize everything?
1 al 21 y 2.
I think, sir, we will
In
wait
conclusion,
for him to finish.
SP32 based platform for multi-zone monitoring and control of propagation each chamber was designed, simple and experimental y valid. The platform integrated environmental monitor, automatic control, local data stranger, Wi-Fi communication y monitoring via web interface y wide interface. I will elevate agriculture. The experimental result show the highest is possible in the main stable elemental conditions and generated for more the hard 40 to 7 elemental as operation records during the experimental campaign. Y pues sería todo las reference y thank you for your attention.
Thank you, Zero, and thank you very much for your presentation. I think your work is more like a project, right? You combine so many things and put together at one place, right?
Thank you for you.
Yeah. So no question from our side.
Attention.
Over to you, Kelvin, sir. If you have any question, please ask.
Dr. Kelvin, any questions, or I will move forward then? Okay, so I think there are no questions. So thank you, Zairovan, for your presentation. And we will move forward with the next one. We have Olivier Zongo. Are you present in the session, Olivier? Or any of his co-authors on behalf of him? Wait, I can see Olivier in the meeting. Are you able to hear us, Olivier? Okay, so we will call him once again after the presentation, after the next one. So next.
Good afternoon.
Good afternoon, Olivier.
Yes, I'm here. My screen is visible.
Yes, it is visible. You can start. Remember, you have 10 minutes only, okay?
Yeah. My name is Olivier. My name is Olivier Zongo from University Najiboni and Burkina Faso. Today, I will present how I work on the automatic classification of obstetric ultrasound sequence using a method we call the temporal quality. This is a joint work with my colleague Somda Mamadou Tiara and Professor Siri. The following, this talk is organized as follows. I will first present the clinical motivation, then our method, then the result, and finally the clinical implication and future work. Ultrasound is a widely used and obstetric because it's safer, non-invasive, and low cost. However, acquiring a good ultrasound image is very operator dependent. In clinical practice, the physician analyzes the continuous video stream, not isolated image. The problem is most deep learning systems treat each frame independently using two-dimensional CNN. This means they ignore the temporal context, the dynamic of fetal movement, and anatomical transition. How core insight is diagnostic validity live in the temporal dimension. And in a low resource setting like Burkina Faso, automating this validation can directly reduce maternal morbidity. How contributions are. The first, a temporal quality gate framework. We validate the ultrasound plane before any automated classic measurement. Second, the tier LSTM architecture, a CNN combined with LSTM and a temporal attention mechanism. Third, a two-phase training strategy adapted to small medical dataset. And fourth, interpretability from frame level, attention, head map, and grade count. Looking at the literature, frame levels, two-dimensional CNN are fast, but they use majority voting with in-your frame ordering. 3D CNN and video transformer capture the temporal information by their computational EV and require large data set. A standard CNN LSTM model use the final ident state, giving equal white, noisy, and clearly frame. How tier LSTM addresses this by learning dynamic white for each frame. We use the intrapartum iteration grand challenge 20 and 24 from MICA 20 and 24 challenge, a collection of intrapartum transpineral ultrasound video. We selected 434 and 34 labeled sequence and reformulated the test as binary classification. Class 1 is a standard plane where the pubic surface is clearly visible and the frame is valid for angle of progression measurement. Class 0 is non-standard, anchor probe orientation, acoustic shadow, and transitional frame. We use five-fold cross validation with strict patient level splitting to prevent data leakage. Here is how our LSTM architecture. Step 1, for each frame in a sequence in 7 and 16 frame, a pre-trained resonator extract a 512 dimensional filter vector. These vectors are fed into step 2. The vectors are fed into an LSTM with 256 ident unit. We capture the temporal dimension. Then our temporal attention mechanism compute a vector alpha for each frame. Step 3, the white context vector is passed to a sigmoid classifier. That is a mathematical formulation of our model. Instead of using the last LSTM state, we compute a vector sum of whole hidden states. Higgs framer receive a score called energy score based on its diagnostic relevance. Their score are normalized using softmax to get attention white alpha. The final context AC attention is the white the weighted combination of all LSTM identity. Why is this useful? Because the model learn is focused on on framework where the pubic surface is visible and to in your framework with motion blur and acoustic shadow. And these weight are directly visualizable, which give a clinician a way to verify the model decision. Training strategy. The handle to small side of how data set we use to phase training strategy. And first when the first five epochs the ResNet 18 backbone is frozen. Only the LSTM and attention layer are trained. This gives a recurrent head a stable initialization. And phase two, the epoch 6 to 20, the entire network is unfrozen for end-to-end fine-tuning. We use differential learning rate. We use differential 10 to the minus of 5 for CNN backbone and 10 to minus of 4 for the recurrent head. The strategies give us a significant accuracy gain, and we will see in the ablation. Now the result of our model. On the ultrasound Grand Challenge 20 and 24 dataset across 5-fold cross validation, how to LSTM achieve a mean test of 95.63% compared to the 94.12% to raise that baseline. A mean AUC rock of 9.89 compared to the 0.972 for the baseline. The inference latency is 14 milliseconds per second, fast enough for real-time clinical use. Statistical sequence was confirmed using the DeLonge test with P less than 0.05. Yeah. The result per folder, if we say looking at each fold individually, the results are stable. And in the best folder, fold free, we achieve a 98.185% accuracy and with zero false positive. And fold 5, the AUC rocker is perfect at 1.0. Training curve and confusion matrix. On the left, we see smooth training and validation curve confirming no overthink. And on the right, the confusion matrix for fault free show the near perfect classification with zero false positive. The rock curve for all five folders show strong
Olivier,
discriminative.
sorry to
Yeah.
interrupt. A quick reminder, you'll have to wrap up in next 1 minute.
Yeah, I will conclude. I will
Summarize
no
everything. Yeah.
Yeah, no. That is the result of the. Um, to summarize, the tier LSM achieve AUC rocker 0.989 test accuracy, 95.63% at sensitivity 97.8% and specificity. All strict patient level 5-fold across. The 14 millisecond inference is compatible for real-time clinical deployment. This work is part of ongoing research and paper to focus the explainable espacio-temporal attention model for quality gating in intrapatum iteration video stream, prepared to John segment based estimation for AOP and head selfie distance from intrapatum US image. Thank you for attention.
All right. Thank you. Yeah, so I just want to ask one question. So, in your thank you very much for your presentation. That was a very nice presentation, actually. All right. So, I just want to find out one question. So, can this your
Yeah.
model be? Can it work in real time? Can the model that you are
We are
doing? Yeah,
not
yeah.
testing. Mm.
So, can
I'm
it
not
work in real
understanding the
time?
question. The
Is
model,
that
this model,
yes? Can it
yeah,
work in
no,
real
we
time?
are not testing the real time. That is the testing, and we will not book. We are not testing in the real time. But this is how this is project. This
Oh, okay. All right.
yeah.
All right. Okay. So, okay, then that's fine because of time. So I don't want to be asking plenty questions. All right. Maybe I would like my co-chair to also ask if he
Yes.
has some questions.
Thank you very much, Oliver, for your presentation. It was a good presentation, and your work is also very good. Right. I want to
Yes.
ask you only one question, that when you collected the videos, right? You have collected the videos, right? So, what was the length of the videos? It was all video stream was of the same length or different length? Because when the length will be different, your result will be different, I am sure. Because uh, you are checking or you are working on a different kind of ultrasound waves. So their
Yes.
sequence length is very much important. So have you checked
Mm.
that also? You are muted. Please unmute yourself. Unmute yourself. Yeah.
Yes.
Yes, I'm not understanding the question.
Actually, you collected the lot of videos, right?
Yes.
Yeah. So I want to ask you that thing that here in your case, since you are working on ultrasound sequences. So in that particular
Yes.
sequences, are all sequences of was of the same length or a different
Mm.
length?
There are different lengths. We use a T or we use a CNN with a equal to 16 frame. Each video has very different lengths. Yes.
Okay. So what was the region in which you can say that your third fold is giving the best result? What was the region? How you tuned your model?
Mm.
See,
Wait,
your model, your TLSTM model is giving us the best
yes.
result in model
Yes.
that is in fold 3. So what was the reason? What
Mm.
was the reason why it is giving the best result in fold 3?
Yes. 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 Why? Yes.
So what is the reason again? Just explain that.
Um, uh,
Have you understood my question?
no. No. No.
Actually, when you see, when you show on your results, in that result, you are telling that fold 3 is giving you the best result in TLSTM model. That is your
Yeah.
work, right? So what is the reason behind that? Why it is giving the best result in fold 3?
Yes.
So what is the reason? I am asking, what is the reason? Why it is giving you the best result in fold 3 only? Why not in fold 1,
Uh,
fold 2, fold 4, and fold 5? Why it is giving in fold
yes.
3? What was the
Well,
reason?
for free because it give the best result.
Yeah, so that I am asking you. This is my question. Why it is giving in fold 3? What kind of adjustment you did in that particular model fold? So it is giving you the best result.
Yes. Um,
Understood or not? Is there any
mm,
effect of epoch on that?
yeah.
Because of that, it is giving you the best result.
Mm,
It's okay, no problem. Thank you, Oliver.
No problem. Thank you. Thank you.
Okay, thank you so much, Oliver, for presenting. So, our last presentation for today is Salma Zowini. She's here to present her paper titled as Integrating Artificial Intelligence into Statistical Process Control Towards Smart and Autonomous Quality Systems in Industry 4.0, a case study on the Tennis Eastman process. So, are you present in the session, Salma?
Yes, yes, I'm here.
Yes.
You,
Yes.
you see my screen?
Uh,
No.
yes. No,
Great.
actually, the presentation is visible, but the presentation is not visible. Sorry, in the meeting is visible.
Okay.
Yes. So you
Yeah,
just
I'm
have
gonna.
to click on the presentation window after you click
Yes.
on the share screen button.
And now you can see.
Yes, it is visible. You can start. Remember, you have 9 to 10 minutes left, so you can start.
Yeah. Good morning, good afternoon, good evening, everyone. It's a pleasure to present this work at Sword SCAT S4 2026. I would like to begin by thanking the session chairs, the moderators, and the member of the scientific committee, and all of the participants joining us today for their time and attention. My name is Salma Zwini. I'm a PhD student at INTA, University of Hassan II, Casablanca, Morocco. Today, I will present our work on integrating artificial intelligence into statistical process control, validated on Tennessee's Eastman process. Let me start with why this matters. Statistical process control has been the backbone of industrial quality monitoring for nearly a century, but classical methods are reaching their limits for three reasons. First, they rely on fixed threshold and Gaussian assumptions that simply don't hold in modern plants. Second, Industry 4.0 brings high-dimensional correlated sensor data from IoT connected systems. And third, even multivariate extensions like PCA T-squared still assume linear relationship, which breaks down for complex non-linear processes. So the real question becomes, can we combine the statistical rigor we already trust with the flexibility of machine learning instead of choosing one of the other? To answer that, let's look at what the recent literature has tried. Several recent approaches have tried to bring AI into SPC. Machine learning classifies like the ones reviewed by Tran reach detection rates of 90 to 100%, far above classical methods. Deep learning goes even further, report an F1 score of 0.795 using pre-trained neural networks, but look at the limitations column. Each of these approaches solves one problem while creating another. ML classifies lack of unified interpretable architecture. Deep learning needs synthetic pre-treatment data, and kernel-based methods need labeled faulty samples that aren't always available. And smart SPC framework, while conceptual appealing, offer no quantitative validation at all. And Colosmo and Colex summarized this perfectly back in 2021. The predictive direction isn't choosing between statistics and AI, it's combining their strengths. That exactly the gap we set out to fill. Without needing synthetic data, deep learning, pre-training, or complex kernel optimization. So here, what we built, our framework is a six-stage closed-loop architecture inspired by the PDCA improvement cycle. Data comes in, getting pre-processed, then reaches the core of our contribution. Stage 3, the hybrid AI SPC layer. Here is how it works. We run two monitoring signals in parallel. On one side, the classical Hotland T-squared statistics, we project the data draw PCA, keep 36 components capturing 95% of variance, and raise an alarm whenever T-square exceeds the upper control limits derived rigorously from the F distribution. On the other side, a random forest classifier 300 trees trained directly on the processed data to recognize fault patterns. Now here is the key. Design choose, instead of using either signal alone, we combine them with a logical and an alarm only fires when both the statistical chart and the classifiers agrees at the same time on the same sample. This single design decision is the entire contribution of this paper, and it has a very intuitive justification, which I will explain. The reason is that these two methods fail in completely different way. PCA T-squares for alarms come from threshold sensitivity, isolated statistical specs during normal operation. The random forest false alarms come from something as entirely distribution shifts when test conditions drift slightly from what the model learned during training. These two failure modes are essentially uncorrelated. They rarely happen at the same time, but at fault triggers both signals simultaneously because it's a real physical disturbance. And the numbers confirm it's a PCA T-square alone falls alarm rate of 0.130, and the random forest alone is 0.301. Even worse. But when we require both to agree just 0.071. Let's see how this plays out on real benchmark. We validate this on-genesis Eastman process, a widely used chemical plant simulation with 52 process variables and 21 documented fault types. We selected 5 representative faults covering different severities and onset characteristics from a simple feed ratio set change to a more diffuse random feed variation. Our experimental setup followed standard practice, 500 normal training sample, 960 test samples per scenario, and 5-fold cross-validation to confirm the random forest robustness before testing. Now the results. First, let's confirm the statistical base actually works. On the left, normal training data. The T-square statistics stay comfortably below the control limits across all 500 samples. No false triggers, which validated our baseline. On the right, under fault 1, the picture changed dramatically. The T-square specs sharply right after the fault onset at sample 161. And our framework detects is just 4 sample layers, about 20 minutes in real time. That's fast, and it's consistent with the published results on this same benchmark. But statistical detection alone has a cost, and this is where the AND logic proves its value. The chart tells the whole story before the fault. Generate several isolation false alarms. Those blue spikes, the random forest is in orange, would fire even more often due to distribution shifts, but our AI SPC signal is in green, stay completely silent before the fault, and switch on cleanly and consistently right after onset. Numerically, PCA T-square alone gives us 96.1% detection rates, but 13% false alarm rates. Random forest alone catches everything, 100%, but the cost of 30% false alarm rates, which inevitable in practice. Our AI-driven SPC keeps the same percentage detection rates with the same 5.4 sample delay, but cuts the false alarm rate down to 7.1. The detection is only half the job. Operations also need to know why an alarm fired. And then, this is where our approach has a real advantage over black box deep learning models. At the moment of detection for fault one, our variable contribution analysis ranks process variables by their deviations. The top three, stripper steam flow, reactor column temperature, and the compressor recycle valve mapped directly onto the no physical signature of federation disturbance.
Salma, you will have
Yeah,
to wrap up in next 1 minute as it's already 10:30, post 10:30.
I go to the and
You
hit
can
the
just
light.
summarize. Yeah, yeah. You can just summarize.
Just to summarize, I can say that by combining a statistical control chart with a machine learning classifier through a simple logical AND, we achieve a 35% reduction in false alarms with zero loss in detection performance without needing synthetic data or deep learning pre-training. And that's all.
Thank you
All
very
right,
much.
thank you, Salma. Thank you
Yeah.
for your presentation. That was a very nice presentation and very good slides also. All right, so I want to find out how did you split the data into the training set and then the testing set? How did you split your data into these two categories?
Is the principle of Genesis Ismail process. It simulates a realistic chemical plant with 52 variable and 21 documents fault types. But for the fault that I chose, as most I took 4 is I took the most important, like uh, temperature and what can I be useful in industry. Can you hear me?
All right. Thank you, Salma, for that explanation. All right, so I can hand over to my next
Yeah, thank you, Salma,
to
for your
ask
nice
question if he
presentation.
has.
I want
Thank
to
you.
ask you about the data set. You are using very small data set, right?
Yeah,
So why you
just
have,
for
yeah,
yeah.
I think that is your limitation, right?
Yes, 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 sir.
Yeah.
I
So, you are using the small data set. So why you have not created more synthetic data sets so that your work will be more and more validated? Or
yes,
yeah,
I work on it
mhm,
to to explore and apply the tennis assessment process with the
yeah,
20 all data sets and all false
yeah,
data.
yeah.
Yeah,
That is better, and that is
just
that is your primary data, huh? From the chemical plant, you have taken that data. So that is your primary data, or you have taken from somewhere as a secondary data set.
it just for this article, this paper, and
Okay.
actually
You have not
I'm
built.
working.
You have not built
Yeah,
your data set.
no,
Okay.
just to validate uh, my
Mhm.
research.
Okay.
Really.
And similarly, at the same time, you have not implemented this in a real industry setting, real-time industry setting. You have not implemented your model.
No, we validated just on simulation benchmark, and I state that explicit Yeah, I don't apply it in industry.
Okay. I want to ask you one more question, that when you were showing us the literature review, right? In that particular slide, you were showing in 2021 work, right? And you are telling that there are some problem like kernel optimization is not there, right? So how your this work will enhance the optimization of kernel? So how you will get the optimization in kernel? That is my question with this particular model that you are proposing.
Mhm. I don't actually practice in kernel. That's is the first application that I use, but in the
No, but you should have some justification, na? If you are
yeah,
getting the best result as compared to the traditional one, right? Traditional system. So how your kernel will optimize in that particular scenario? Because you are already taking kernel optimization will be better. That is not presented in 2021 paper. So how your work will optimize the kernel? That should be there, na?
actually I use a random forest for the moments. That's
Mm-hmm.
for because that's what I need. The strong performance without extensive tuning and robustness to noisy industrial data, and feature imports that integrates naturally with our variable contribution analysis. That's why I just
Okay.
yeah.
Okay. Thank you, Salma. Thank you very much. Thank you. Over to
Thank you,
you,
sir.
Yashita. Thank you.
Yes, sir. Thank you so much, Salma, for the presentation. And that was the last presentation for today. So I think we are good to conclude now. And on behalf of Global Knowledge Research Foundation, GIA Scholastic LLP, and the entire World S4 2026 organizing team, I sincerely thank all the authors for their excellent presentations, valuable research contributions, and active participation. A big thank you to all our attendees for making this session interactive and engaging. Your presence truly made a difference, and this is the 10th edition of World S4. We deeply appreciate your continued support over the past years, and we look forward to welcoming you again for the 11th edition in 2027 as well. And there are a few important announcements to make. All presenters will be receiving their digital certificates through their emails within 2 working days, and the conference publication is expected to go live within 7 to 8 months. And we kindly request your cooperation with the World S4 team throughout the publication process. I would also like to express my sincere gratitude to our respected session chair, Dr. Basant Tiwari sir, and Dr. Kelvin. Thank you for joining the session, both of you. And this is a small token of appreciation on behalf of the whole conference team. And once again, thank you everyone for your valuable time and participation. Also, there's one last request. Could everyone please switch on their cameras so that I can take a quick snapshot of this conference as a memory? Yeah, Vedika, Olivier, I request everybody please switch on their cameras. Yeah, thank you everyone
Thank you,
once
man.
again. Stay safe and have
Thank
a
you,
wonderful
Ashita.
day
Thank you,
ahead.
everyone. Thank you very much. Have a good night. Have a good time.
All right. Thank
Thank
you
you very
all.
much. Thank you very
Thank
much,
you
Kelvin
all.
sir. Thank you.
Bye to everyone.
Bye, sir. Bye. Bye, sir.
Bye.
All right.